Thank you very much for coming to the second seminar of the semester. It's an honor to introduce Dimitra Panagou. She's coming from University of Michigan. She got her PhD, both a diploma and PhD from Athens in Greece. And then you did a short postdoc at Illinois. And then since 2014, she's been at the Department of Aeroastro and the University of Michigan. She's a controls person, that's what she says, worrying about risk management and safety. And this morning she was saying that she's been gradually drawn more to robotic systems for two reasons. One is interesting aspects of human-robot collaboration and how do you make guarantees about those systems as well as learning systems. So it will be great to hear about some of that. Thank you.
Thank you very much, Alberto. Thank you very much for coming to the talk today. So indeed, the core of my research as a PhD postdoc student and as a faculty at the University of Michigan is multi-agent planning and control. So I'm interested in algorithmic developments for provably correct solutions for problems that involve many vehicles. The main application is ground, marine, aerial, space vehicles. So here, what I have put on those slides are essentially the cartoons of some of the projects that I have been working as a faculty with my students that are related to autonomous surveillance and exploration with unmanned aerial systems in uncertain environments that might be populated with adversaries in the sense of agents that might be hacking your network and trying to inject malicious information and send wrong information to the network, as well as systems that are, again, multi-agent and are closer to the traditional aspect of traffic control and aircraft deconfliction for the future unmanned traffic management system and how we can safely integrate our UAVs in the national airspace to environments of self-driving cars. And again, the environment here are agents that might not be necessarily adversarial, but still might be causing collision and violate safety with respect to your own car. So within this variety of applications, today I would like to talk more on the focused research that is more tailored to robotics, which is human-robot interaction. And this is something that is a fairly new direction for my group. The motivation has been a NASA grant that is related to space exploration through human-robot interaction. And before going there, I would like to emphasize that our work tries to, motivated by realistic problems, come up with sufficiently abstract structures for describing our networks and multi-robot systems and the information flow and their objectives that have to do with safety and resilience in order to come up with provably correct solutions that are applicable in uncertain environments towards advancing autonomy. So with that, well, essentially, this is, and I'm pretty sure, apologize for this bar, it cannot go away. But essentially, this is the type of, some of the projects that we're currently running. I have 5 PhD students. The picture shows my PhD students through one of our flight trials at MER. MER is a new big outdoors facility that is available at the University of Michigan. I also have 2 postdoctoral researchers and a couple of masters and undergrads. Some of them are being busy with primary focus on how to ensure safety for self-driving, for interactions on the highway. And we do that with the core of our tools is what we call multi-agent barriers, which is for ensuring safety. What we are interested in further doing is how to make those multi-agent barriers that essentially generate safe controllers for our multi-agent system be resilient against malicious information. So in this video, you get to see 2 agents that are bad because they are adversarial and they are trying to send bad information to the network, trying to lure the good agents away from their nominal positions. So we're interested in how to make those guys move, achieve the consensus-based formation in the presence of those malicious agents. So hopefully I will talk about that in the second part of the talk. Here is the more robotics applications that have to do with how we fly in order to gather data for autonomous exploration. And this is one of our demonstrations in, outside our aerospace building on the North campus. And again, when it comes to barriers, you can consider disturbance rejection. You can consider various deconfliction objectives, and particularly in finite time. This would be finite time if you could see it fully. But I will start, so this would be second part of my talk. I would like to start with a human-robot interaction, which is a little bit different than those collaborative objectives for multi-robot systems. What we do is we have multitasking environments for a human, and we would like to come up with ways of how a robot, like an aerial robot, could be a good assistant to the human by deciding, learning on its own and deciding which task views would be more useful to the human in order to execute this sequence of multi-objective tasks. Okay, so I will show the video again towards the end of the technical details. So let me cut it here and show what is the block diagram of this study that we are conducting. So the motivation, as I said, came from space exploration, how you can design swarms of intelligent space robots, like space-free flyers, in order to assist astronauts with their EVAs and IVAs, extravehicular and intravehicular activities. Okay, so that is the cartoon, but essentially what we need in order to be able to come up with these algorithms is ways of understanding what is the intent of the human, inferring what is the intent of the human based on current observations and possibly also prior models about how the human behaves in an environment. The learning strategies with which robots can understand and build knowledge about the intention of the human, and with intent we essentially mean high-level goals. Okay, so the human is supposed to go among locations to execute tasks. The intent of the human is which location I want to go next. Okay, it's that high-level abstract consideration of what the human intent is going to be. So once you have the models that describe the motion of the activity of the human and the robot and the prediction of the next positions of the human, then this information can be used in, between the co-robots in their own task planning and control according to some criterion of what is going to be useful for the human to do, how they're going to be useful to the human, okay? So, in this project, we started in a sort of, maybe you can think of it as a reverse way. We first focused a lot on the swarm motion planning and control, meaning if you have some high-level objective that has been determined for you, maybe by the instruction of the human or some other means, then how you can make robust, how you can do the path planning and the coverage in cases that have to do, for example, with exploration of the exterior surface of a spacecraft. So this is work that we're doing on dynamic coverage or data exploration. I'm not going to talk in detail in this seminar about how to formalize this problem. I just want to reinforce that coming up with solving the problem for how your swarm can move autonomously, then the challenging problem is how these strategies can be integrated around the human and be able to, so that you come up with realistic solutions for for a human-robot interaction, you want realistic prediction of how the human is going to move. And this is how we spend our attention thus in order to come up with models of, with inference methods in order to understand what is the next best, most likely location for the human and in a sequence, among a sequence of tasks, and so that the robot picks what would be the next best position for the robot that overall minimizes the shortest time, minimizes the time to task completion. Okay, so so you can use inference in order to predict human activity, but you might want also to think of it as a problem of learning online the human activity and the robot policies, which is what we are currently working on in this project. And this is the video, this is summarized in the video that I will show you again at the end. So just again, the context, we are interested in particularly coming up with ways of how these space-free flyers, which are the future astrobees that are going to be launched on the ISS this coming April, can be used in interaction with a human in order to assist in various scenarios. The scenarios that we have considered are the environmental monitoring, which is the external inspection, autonomous inspection that I showed you earlier, and helping humans with multi-task objectives, which is what I'm going to describe in detail right now. So, okay, so some extra motivation is that NASA has already started evaluating this type of assistive techniques and technologies on the ISS, like using augmented reality environment setups, like the Microsoft HoloLens. And that is what we primarily motivated us in order to design this exact setup. Okay, so as I said, we have the human executing a sequence of tasks. Think of it as the human being here executing an assembly task on location I2, which is some desk. In our experiments, we have human subjects assemble a toynet kit. You have the instructions of this assembly task at some part of the room, which is location I3. And you also have some secondary objective, which is denoted here at location I1, which is a light that turns on at random times, okay? That is determined by a Poisson process. So, the activity that we are trying to model and have the robot learn online of the human is that in such type of environments, as the human is executing the task, they're going to split their attention between the main objectives, okay, which is going to be locations 1, 2, 3. So the problem is how to have the robot monitor the human without knowing a priori where these locations are, trying to understand what are these three, as many locations of interest, try to understand where are these locations of interest, of visual interest, as we say, of the human, and make decisions on which task location to take a video of with its onboard camera, such that this video is streamed on the human's augmented reality display, okay, like a HoloLens head-on display. Why we do that is we want to understand whether such assistive views that are learned online by an intelligent agent like the quadrotor can help quantitatively the execution of the mission for the human in terms of reducing the task completion time and the head motion. Okay, so the human has to move around their head as they are executing their task without the assistance of the robot. So how much better this process can be done with a robot transmitting assistive use, and which assistive use to transmit, if at all, to the human. Okay? And then in a sort of qualitative way, we want to understand whether the perceived efficacy, comfort, and naturalness, if at all, of this interaction, how this is perceived by the subjects. Okay, so what we have done up to now is to model the human visual acuity using functions that are truncated Gaussians with parameters that have to do with the field of view as obtained by physiology books, such that we have a good forward-looking model of the capability of the human, of the viewing capability of the human. And similarly, we are considering also a sensor model for the robot camera, for the forward-looking sensing capability of the camera, that is kept in an abstract level, in the sense that we have this forward-looking cone of view over which we define this functional SR, S sub R, which takes non-zero values inside the cone, and it encodes that within that cone there is an anisotropic sensing capability for the robot. So you can view anything in that cone, but not with the same quality at each point, and it's zero otherwise. Okay? So we want to encode in a very abstract way that your visual capability degrades as you go towards the range, the boundary of the range, and towards the limits of the field of view of your camera, of your onboard camera. So okay, you have that, and then the question is, what can you do with that? So essentially, over the experiment, as the human is moving their head around in order to execute the task and view the instructions and observe their secondary process, which is turn off the button when it becomes on. We have the visual capability, the visual acuity of the human, the sensing view, the cone view of the view cone of the human, moving over space and time, and that can define this activity model, okay, the visual activity model denoted by this Q functional here, which is essentially the raw data that we have available about where the human views. So essentially, as we are conducting our experiments, we have we model based on this abstract sensing viewing cone, what are the elements, what are the points in the environment that are viewed by the human. These are our raw data that we use in computing Gaussian mixture model, whose mean values are going to be the locations of the most likely locations of the tasks. So in order to be able to run this algorithm, we assume that we know the number of the tasks, such that we know that we are fitting a Gaussian with that many, a mixture model with that many Gaussians, but we don't know where they are located. So having now this information shows where the human is putting their visual interest over time. And the question is, okay, then what should the quadrotor do in order to be useful to the human? So the very first approach that we followed in order to close the loop with a quadrotor, which is maybe a naive one, I would say, is have the quadrotor try do essentially gradient following follow a gradient-based controller, which has the effect, essentially, of making the sensing cone of the quadrotor sweep in the environment, such that the sensing quality obtained by the quadrotor is matching the value that you have out of your visual acuity of the human, okay? So essentially, the quadrotor tries to align itself, the cone, with wherever the human is going to spend most of its time. So once you have your objective functional in this exact form, you can take first order time derivative, which is going to make your system dynamics and the control inputs of the quadrotor appear. Long story short, you can pick a controller for the quadrotor such that this objective functional is trying to be minimized, and this is going to make your quadrotor move around similarly to what we started seeing in that video. Okay, so these are our first results that we will be presenting in the upcoming ICRA. And so to summarize, what we would have done is that we ran a smaller case study of about 10 subjects, and we model the motion of the subject as they are executing these multitasks scenarios. In this smaller scale experiment, our head-on display was this glass, this view-fine glass camera set, so not as ergonomic as a HoloLens. And so we have this human assemble the toy kit while the instructions are to their left, and the button that will be flashing at random times is toward the right. So both of them are out of their field of view when they are spending most of their time in the assembly task. So as you get to see, what we do in the beginning is we have the the expectation maximization algorithm run for a while before the quadrotor gets into action to assist the human, such that we first learn a little bit the locations of the primary objectives, okay? So once we have the model of the human activity, the quadrotor is deciding, and again with just a gradient following controller, so it's a very reactive controller, is deciding to split views, as you see, between the instructions over here. And so here it is spending more time on the instructions because it understands that the human would want to see the instructions for a longer time as they assemble the task. We have killed out the effect of the assembly task because the human is always looking forward anyways. And from time to time, the quadrotor is also going to rotate to show you, here is the button that the human will have to turn off at random times. So we ran those experiments with, as I said, about 10 subjects. And on average, as you expect, the head motion was reduced because the humans could see on their head-on display the button popping up. We have, maybe in a counterintuitive manner, we found that the average time to accomplish the task with the use of the quadrotor increased. So we had each one of the subjects do 2 assembly tasks with the aid of the quadrotor assistant and without the aid of the quadrotor assistant. The average time didn't increase. And we think that one of the reasons is that the head-on display was so small to see the instructions in there. So this is the verification of the data, as I showed. And one thing that it struck our attention, which again, this is in a very small scale study, but we noticed that almost all subjects did like the assistance by the quadrotor in the sense that their head motion and their head motion reduced. That's the good metric that did reduce. Except for this middle subject happens to be an artist. The other two subjects are engineers or computer scientists. So we thought that maybe people that are already trained more in this type of technology would like that type of assistance more than others, that they just feel that it is confusing. Okay, so definitely we didn't like the display, or the subjects didn't like the display, and that was also in our plans anyways to substitute that with a Microsoft HoloLens, so that the view that we get from the streamed view of the quadrotor is much more ergonomic, much better in the field of view of the human. And we are now executing the same. We also have a lot of how good the result is going to be. Obviously, depends upon what the human activity model you're building, which depends a lot upon where you think that the human is gazing, which depends a lot upon the measurements that we have about the human field of view, which depends a lot upon the motion of the orientation, essentially, the attitude of the head. And instead of just computing that based on our sensor model and Viacon, we added the Intel RealSense sensor on the HoloLens in order to get the depth cloud. And as well as eye trackers in order to understand, to better to track the pupils of the subjects and have a better and better data in order to more accurately localize the locations of the tasks. So we are running a new studies with more subjects. We have an IRB approval and everything in place, and we have collected data from about 50 people up to now. If you ever come to Michigan, please stop by our lab, because we will love to get your data as well. And we also do something more. We allow, essentially, reinforcement learning. We allow the quadrotor to learn from instructions and rewards from the human, instead of just using this type of essentially reactive gradient following controller of this objective functional. So how we do that, we again have the experiment run for a while in order to build the locations of the tasks, so that we have so that we can essentially work with an MDP rather any POMDP, and then we take into account also the sequence of the tasks instead of just considering zero memory. So we have a higher ordered MDP there that we are trying to incorporate in how to do the computation of the policy. So we are considering up to 3 tasks in order to keep things computationally efficient. And we consider the last 2 tasks that the human has observed, that the human has observed in the sense of has executed, the last 2 tasks that the human has executed, which means that from there, so for example, if you are in, let's say, the ABC transition, then that means that from C, with AB, you can go to either B or A. So your next state is going to be, I was prior in BC, either B or BC, A. Okay? So that would be the Markov chain, that the Markov process that is determined by such a consideration. And on the online execution of computing the robot policy, what we do is we implement a Q-learning algorithm. So as I said, we let the human visual interest build for a while until we have a good enough model of the GMM, of the task locations via this GMM. And then we launch the robot. So the robot will do a mix of exploratory and exploitation maneuvers in order to trying to compute what would be the epsilon greedy policy. And the reward, so the interaction that we have incorporated in the experiment is that the human can say to the robot, essentially to my student, whether the view that it's getting right now from the quadrotor is good or bad. So this is locked also as a reward in the training of the policy. And so the human, the human can can train the robot to send it more useful views. We also consider other things in our reward. It has to do with the transition time between locations. So we don't want the robot to go to locations, task locations, and if they are too far away from where it is, because by the time that it will go there and send a useful view to the human, most likely the human is not going to appreciate that view because it will be already too late for the human. So we are trying to come up with finding the best policies by considering this type of rewards, okay? So this is an ongoing research study, as I said, and we hope to have more results within the next few months, and be able to assess whether now our training policy is going to give us even better results compared to the first initial results that we have for ICRA. Okay. So as I said, this is the work that we are doing for human-robot interaction. And I can see my group keep working along these directions for the next years, in the sense that we are very much interested in not only having one robot, understanding, learning what is the activity, the tasks of the human, but rather have many robots do that, so that you can find many interesting problems there on how to even distribute the tasks and do the task allocations between the robots once they have inferred how to help one human. Even more interesting if you have many robots and many humans collaborating in the same environment. So we have students who keep extending this type of work towards these directions. So hopefully, in the next couple of years, you will hear more from our group. So for the second part of my talk, I would like to switch gears a little bit and get more into the multi-agent stuff that have to do with these abstract ways of encoding safety and resilience, and algorithms that have to with which we can achieve mission accomplishment with certain safety and guarantees against bad information. So our idea is that, once you have a network, this network of agents, this could be agents like robots, can be UAVs, can be self-driving cars, but essentially what you have as usually as your problem is that the information that you have, that you share among the nodes of this network might be subject to disturbances from deliberate attacks or just environmental disturbances, sensing disturbances. You might have good agents, you might have bad agents, so agents that don't have the same objectives. You might have goal locations, goal states that your agents should go to, and states that are unsafe, okay, that should be avoided. So the way that we are trying to come up with algorithms that solve these problems is to think, if I have information that over a communication network and over sensors that I have on board that needs to be used in our decision-making process, then essentially I have to find a way of understanding reconstructing the information such that it is useful and can be used for safe decisions. So that's why here in the resilient estimation box, I talk about information filtering. Okay, you have information. Each node receives information from their peers, from their neighbors. You might not know whether the neighbors are good or bad. It might be a neighbor that got faulty for whatever reason. It could be a neighbor that got compromised and you don't know and he's sending you bad information. So you have to do something with that information. You have to filter it somehow in order to make some useful decision with that. Usually, if you think of some sort of leader-follower formation for your UAVs or whatever, that means that you have to follow a reference. So definitely, you want this reference to be something that is reliable, okay? You don't want to follow a reference that is hacked because the reference is going to take you down to the ground or to crash you on a wall. So the information filtering is going to be used for estimating the reference and maybe estimating even the goal state, the current states of your agents and their goals, where they're supposed to go, okay? Where do you want your UAV to go? Definitely not on the wall. So you have to take into account that this has to be done in a way that can bypass malicious information. And then once you have these resilient estimates, you want to use them in your safety control. So your agent will have to avoid collisions, will have to be able to avoid static obstacles, will have to be able to avoid, in general, unsafe sets in your state space, possibly in the presence of even physical adversaries, okay? So you might have adversaries that mess up with your information, but you also have physical adversaries that might be messing up with trying to nudge you, trying to intercept you. And still you want to achieve your mission. Is it always going to be possible? No. We're trying to come up with conditions and ways of trying to make it possible, trying to enable it when possible, okay? So I will be talking about resilient estimation over secure communication topologies and a little bit about our safety control. And I will be very happy to talk offline about our newest results on control barrier functions, maybe later at the end of this seminar. So, okay, a little bit of motivation. Again, you might have networked vehicles that are subject to adversaries that might compromise you, and that can be viewed in various physical systems. What do we care about? We want communication to be resilient, meaning you want to have communication structures that can guarantee that under the correct, under sufficient, if you wish, estimation and control algorithms, they're going to essentially tolerate the malicious information from potential adversaries. And with this communication structure, with this malicious information, you want to make decisions on how to move around such that you can still maintain safety. Okay, so in a sense, I'm interested in integrating the resilience and the safety aspect that it's quite interesting, particularly in dynamic, in mobile networks, where both physical motion and where physical motion affects both the communication and the safety aspects of the vehicle. Okay, so what do we do? In a nutshell, when it comes to resilience, we follow the work that, the usual tools that we have in order to model networks as graphs, either directed or undirected. So the results that I'll be showing you hold both for directed and undirected graphs. And we are going to consider that this network that has up to n agents, up to f of them might be adversarial. Meaning, what do we mean by adversarial? Adversarial means that for whatever reason, they are not going to play the nominal strategy that the other agents are going to play. And so either or, they're not going to share their actual states, okay? So they are sending wrong information to their neighbors. Either the same to all neighbors or different to different neighbors, it doesn't matter. They don't play nominally, that's the bottom line. We do not know who the adversaries are, but we know that there is a bounded number of these adversaries in our network. So under which conditions can we have resilient communication graphs is our first question. And again, this is work in the literature, so it's not something that we discovered. But it is already established and well known that in order a sufficient condition in order to have resilient consensus is that your communication graph is robust, or a variation or similar notion is called RS robust. What does R robust mean? Essentially, that means, per the definitions that you get to see on the right-hand side, is that essentially every node for all possible combinations of sets that you might define in your network, each node is R-reachable, which essentially means that it has incoming connections outside its own set. Okay, so essentially it has sufficient information coming from the outside. Okay, so if your graph has this property, then people have developed this type of information filtering that I was talking about, which works as, okay, the idea is that each node, each agent is going to receive the information from its neighbors. The neighbors might be good, might not be good. The way that the information is filtered or is treated is that you sort the information relatively to your own state. And what you do is you chunk out the F highest and the F lowest values. Okay, so it's like chunking out the outliers with respect to your own state. With that remaining information, you play your control strategy, let's say consensus, it goes over the agent dynamics, the network updates their states after a certain point, and so on. Okay, so what is nice about that? The nice thing about that is that you, without knowing who your adversaries are, if you know that they are up to F in your entire network, then you can guarantee consensus if your network is 2F+1 robust, okay? So essentially that means that if you want to tolerate the effects of up to F adversaries without knowing who they are, then you want to talk to sufficiently many agents, essentially each node to be reachable by 2F+1 nodes, okay? So it gives you essentially the structure, the design that your network can have such that you can achieve consensus in the presence of malicious information. Okay, so that's nice, but that comes also with challenges, okay? So up to here was work that was state of the art when we started working in that area. And the challenges coming to the picture by the definition of the robustness on its own, in the sense that you're essentially, in order to determine the robustness of your network, you have to check all possible combinations of disjoint sets that can be formed in your network and see what is the maximum number of incoming neighbors for each node under all these possible disjoint sets, under all these possible combinations. Well, that's going to be hard to compute. And in addition, this type of resilient consensus is going to give you robust convergence to some value in the convex hull of the initial states. But once it comes to problems that have to do with constructing reference signals to be used for path planning, for leader-follower formations, and so on, then you want to essentially have consensus in the presence of consensus to a reference signal, consensus to leaders. And as we saw, just applying the existing methodologies to leader-follower communication strategies does not extend directly. You have to be careful on how to design your leader-follower communication strategy. Okay, so what we had, so what are our contributions in this part of the literature? So we started by first studying specific communication strategies and guaranteeing that they have the desired level of robustness such that we have a constructive way of providing networks with predetermined level of robustness. So, for example, K-circulant graphs, we proved that they are robust where R is K over 2, so their R robustness depends upon the number of connections between agents K. And we also started considering problems that have to do with resilient consensus to arbitrary reference values for formation control. So this is the application of our algorithms in the case of having leaders being the blue agents, followers being the black agents, and all the others with the X's are bad agents that they send wrong information. Our algorithms are such that we can guarantee that the good agents, without knowing who they are able to reconstruct the reference signal from the good leaders without knowing who they are and converts to their formation locations. So I will be briefly talking about that in the last 5 minutes. And as an additional note, we have, in order to determine now robustness of arbitrary graphs, because it is very crucial property for determining whether your network is sufficiently robust and cannot be compromised in a sense, we formulated a mixed integer linear program whose solution can give us the robustness of the network more efficiently. I'm not saying that we can do it real time, but more efficiently than the state-of-the-art methods, okay? So this is what we are going to be talking in the next few slides. And the idea is that, okay, how you can do the the resilient formation control in a case where you have a digraph, so a directed graph that we consider here to be time invariant. States are the positions of the agents. We consider simple double integrator dynamics here. And the idea is that each one of the agents has a formation vector relative to what would be the formation center. So Ti is the variable for each one of the agents that describes what would be eventually the center of the formation, which essentially means that consensus on the agents on their TIs achieves that all the agents agree or where the center of the formation is, and they go and are placed along the formational offset Xi, okay, in order to achieve their the final formation. So, okay, so in order to achieve that in a nominal setting, each agent would have to receive the relative information Tj minus Ti, and in our case, that information might be hacked, might be malicious. The question is how you can design your system, your network, such that resilient consensus can be achieved, such that you have resilient formation control. Okay, so what is the catch? Compared to a previous resilient consensus work, is that the topology of the network cannot be just robust. It has to be, as we say, as it is determined in the literature, strongly robust, which essentially means that you have essentially to have layers of subnetworks, and with the leaders being the top layer here, and you want to have sufficient connections in between the layers for the flow of the information, okay? So we call these graphs resilient directed acyclic graphs with parameter R, meaning that the parameter R has to do with how many connections outside, in connections, in neighbor connections, each one of your neighbor has with respect to agents outside the layer, the set it belongs to. Okay, so this is the conditions that should hold when it comes to the design, the robustness of the graph. For example, K-circulant graphs do satisfy this condition, or you can run our algorithm to come up with other graphs to satisfy that condition. So you put your network, your agents on such network, and then you apply, and again, you don't know who the adversaries might be, so you update based on the norm of the formational offset between your agents. By what we did is we decided to chunk out the highest values, okay? Because why? And why did we choose that? Because essentially that means that you are filtering out those that are far away from you. Our first approach is that because we could prove that it would work, you can achieve resilient consensus under this control input now. You also see that we have tweaked it to be finite time convergent so that we can guarantee how much time, eventually we can guarantee not only that you will converge, but how much time it is going to take you to converge to the formation. That's going to be useful for integrating safety from there on. But we are also looking into more sophisticated estimation, filtering mechanisms instead of just filtering out based on the norm, okay? So here is just some gazebo simulations. We hope to be able to run outdoors experiments also with resilient formations and in May, because we have also a review meeting. So for now, gazebo is where we demonstrate this type of resilient formations. And to wrap up to now, we have been talking about how to reconstruct essentially your reference signal. Okay, so what is your reference trajectory? The agents the followers are able to reconstruct the reference signal from the leaders without knowing who might the bad leaders be. But as they converge there to those reference signals, we do not incorporate any safety consideration yet. So once we agree on the reference trajectory, we want to make sure that we are going to ensure to use some safety critical controller. And for that, we are currently working on incorporating our barrier functions with malicious information. So you might guys have seen in the literature lots of work on barrier functions. You might also have heard them, all the variations of barrier certificates and barrier control barrier functions and so on. With which you can compute and encode safety critical controllers and encode safety, e.g. collision avoidance among the agents. But in these formulations, you consider that there is no malicious information shared in the network. So in our case, we will have to see how to do that in a resilient manner, okay? So the idea is that, and I will be wrapping up, that we can define barrier functions as closed form expressions in terms of distance and avoidance, distance in terms of maintaining proximity for connectivity if we wish that, and also distance with respect to the formational offset, such that whenever these barrier functions become zero, essentially we have the encoding that the formation is going to be achieved. And then what we have simulated and we hope to prove in the next months, meaning we would hope to complete the analysis in the next months, is that if you pick your controller for each agent, your distributed controller for each agent, such that for the resilient reconstruction of the maintenance of the connectivity maintenance, for the resilient connectivity maintenance, you take into account the filtering, the filtered agents, as I described earlier. And for avoidance, you take into account all the agents in your vicinity because you want to avoid everyone that is around you, no matter whether they are bad or good or filtered or non-filtered. So if this is the controller, then we have promising initial results that the agents will be able to avoid the bad agents. The bad agents here are deliberately static to create static obstacles also. And resiliently, in the presence of malicious information, converge to their final locations, okay? So I will skip. I was not planning on giving that part of the talk anyways, but it has to do with motion planning with finite time convergence. I'll just want to take it back here, okay, to wrap up. So today I talked a little bit about human-robot interaction and our investigation on how assistive views from quadrotors, from robotic agents, can be used to predict human intent and assist humans with multitask execution, as well as our work on resilient estimation over secure communication structures and the integration of safety controllers towards hopefully more safe and resilient multi-agent systems. And with that, I would like to acknowledge the support of our sponsors. I would like to thank you very much for your attention and take any questions that you might have. Thank you.
Any questions?
Hi. With the human-robot interaction and human helpful behaviors, I'm wondering whether there's some considerations to make in terms of, for example, the experiment that you're running. If I were a subject, I would feel that given the state of not having assistance versus having assistance, I would have a different set of priorities on where my attention would be focused, especially with those tasks. For example, if I am doing this by myself, I'm going to glance at the light, but mostly when I'm looking away, I look at the instructions. But if I know that I have something else looking for me, I might want that to be continuously monitoring the light and occasionally looking at the instructions. It seemed to me that the scheme that you're using for the learning wouldn't optimize that scenario. It would optimize looking at the instructions because that's what I would do in the non-case.
So what we have run up to now and that are related to the ICRA paper, then it does exactly what you're doing. That the ongoing experiments where we ask the human to provide reward and say, do you like that? Do you like that view or not? We hope, we anticipate, I mean, the first set of experiments that we have run show that the robot is better trained to the preferences of the human. So, so as you are, as the robot is interacting with you, we would keep reminding you as the subject to tell us, do you like that? Do you like that? Do you like that view? Do you like that view? So essentially, we ask you to always record good, bad, good, bad. So in that case, your own preference that I don't like that, what you're doing right now, is going to be encoded in the policy, and the robot is not going to do something that you do not like. So we don't, I think that if I get so we do not put any priority if this is what we are asking a priori. We let the human train the robot based on their own. So the robot doesn't know anything about the human before.
To follow up on that, is there any concern that, given that this is new information that a human's not used to before, that you might be approaching kind of local maxima in terms of benefit rather than the global maximum, and that I might find a view that I like more, but if I had considered this other one, it could have been significantly better, and I just never realized it because I said, oh, if I go down this path, this is better, and I want to stay here.
That's very likely because that's what it comes with this type of approaches, which is also something that can happen even in our reactive controller, since it is in general a non-convex function. But the motivation for having such a system comes actually from the very unstructured environment up in space, where for an EVA, for example, for repairs. So astronauts, whenever they have to do a repair in the exterior of the ISS, they will have to spend a lot of time in spacewalk, and sometimes even coordinating with the ground station or the interior of the ISS. I need to take a view of this part and trying to localize or reaching something that is hard to access, or even trying to communicate that I want to go left and right. It becomes very obscure in a very unstructured environment. So the idea is that a robot that can understand on its own and with minimal instruction, figure out where to go to help, even if it is not the optimal solution, it is going to be hopefully a assistance, a solution.
Any more questions?
So just following up on the same one, could you show that slide that you have the 6 subjects answer? You have 6 subjects. So the
Should be getting close. That one? Yeah.
Yeah. So the question that I have is that if I understand this, is how much time it takes for you to complete the task. And if I look to the subject that you said that was the artist, the artist finished the task with the exception of the first subject, unassisted, he or she finished sooner than all the others when it was unassisted. The red line.
The red line is the unassisted.
Correct. It finished well before the assisted. So my only comment in this task is that perhaps because the artist was thinking multiple connected pieces that they were going to do when they are not assisted, they do it faster, not because they don't like the technology. So the way you formulate it, you are assuming that there is no interaction. Because you're assisting, the person doesn't change the strategy. And I don't think this...
Yeah, so essentially what I was trying to convey is that the artist didn't see any advantage of using the technology compared to the engineers who enjoyed also, the fact that they had some virtual reality headset and some assistance in this augmented reality, setup with them. So, and again, this is very, very low, a very small case study. Essentially, this is between members of the lab and our friends, because we wanted to first test whether the entire setup works okay in terms of hardware and software, and see if our initial idea would have application as we originally thought.
Right, because actually now that I look to this, it says that of your 6, you have 3 subjects that unassisted completed faster, and the other 3 subjects completed at the same time. So actually unassisted led to completion faster.
For the artist, it's also showing that, and more overall, the scale is that it is about the same, whereas for the others there was, and this is the significant, actually, just to clarify, this is the value that comes with this is the metric that has to do with the rotation of the head motion, okay? So that's why we said that the artist didn't make any difference to rotate their head less or more, or essentially the engineers tend to rotate their head less because they were expecting that view on their head-on display. And overall, for all the subjects, we noticed that the mean time to completion increased with the assistive technology. And that was definitely one of the reasons is that this particular viewfind small view was not ergonomic enough. So the display was so small on that, see, it's just glasses with a small camera. They could see the lights. They couldn't see the instructions. That's why it took them longer. This is our very first conclusion. And that's why we now are trying with the HoloLens.
You might be right, but alternatively is that you change the strategy instead of looking the next piece, the next piece, the next piece that I need to put. I look to multiple, and that's why I'm completing faster.
That's true also. That's a good point. Thank you.
All right. Any more questions? If not, I think that we'll wrap up and we can continue the conversation outside with some drinks. All right?
Thank you very much.